Let's talk about the first isomorphism theorem for groups. So isomorphism theorems are a recurring theme in algebra. We have a similar theorem for all sorts of algebraic objects. Let's talk about one for groups. And it says let G and H be groups, and let theta from G to H be a homomorphism. So theta is a structure preserving map between these groups. And then it tells us that G quotiented by the kernel of theta is isomorphic to the image of theta. So the kernel of theta is the set of all the elements in this group G that get sent to the identity in H. And we know that that's a normal subgroup of G, so this quotient here is a group. The image of theta is contained within H. It's all the things in H that get hit by theta, and we also know that that is a subgroup of H. So it makes sense to talk about these as being isomorphic. So to prove this, we're going to write down a map and then argue that it is in fact an isomorphism. So I'm going to define theta twiddles from the quotient group G quotiented by the kernel of theta into the image of theta, and I'm going to send a left coset here. So the elements of this quotient are all left cosets of the kernel of theta, and I need to send this left coset to something in the image of theta. So the natural thing to do would be to send it to wherever theta sends little g to. Now there are all sorts of things that we have to think about here. So the first thing we have to worry about is whether this map is well defined, because there are potentially different ways of choosing left representatives for left cosets here. So this hedgehog might pick one representative, this hedgehog might pick a different one. We need to know that both hedgehogs are going to write down the same thing for where theta twiddles sends that left coset to. So let's show that theta twiddles is well defined. So why is that? Well, we know that theta, because it's a homomorphism, is constant on cosets of the kernel of theta. That's something that we've proved elsewhere. So theta is constant on cosets of the kernel of theta. You might like to check that for yourself if you haven't thought about that recently. We also need to know that theta twiddles is a homomorphism, that it preserves the structure here. So why is that? Well, theta twiddles of, let's take the product of two left cosets, so let's say g1 cur theta and g2 cur theta. Well, what is this? We know how to multiply left cosets. We know what the operation is in the quotient group. So there's this theta twiddles of g1, g2 cur theta, just by using the operation here. Now we know how theta twiddles is defined. This is defined to equal theta of g1, g2. Theta is a homomorphism, so that's the product theta of g1, theta of g2. Remembering that the operations are happening in different groups, but we'll write them multiplicatively and not worry about it too much. Now theta of g1 we know is theta twiddles of g1 cur theta, and then theta of g2 is theta twiddles of g2 cur theta. So this is precisely the homomorphism property we're looking for. We'd also need to know that theta twiddles is a bijection. So let's show first that it's an injection, and then we'll show that it's a surjection. So theta twiddles injective. Why is that? Well, if theta twiddles of g1 cur theta is equal to theta twiddles g2 cur theta, then that means precisely that theta of g1 is equal to theta of g2, just using the definition of theta twiddles. But theta is a homomorphism, so this implies that theta of g1, g2 inverse is the identity in H. And now we use the definition of the kernel of theta. That means that G1, G2 inverse is in the kernel of theta. That's how the kernel of theta is defined. And by our coset equality test, we know that this means that G1 curve theta is the same left coset as G2 curve theta. So if theta twiddles does the same thing to two left cosets, they were in fact the same left coset. So theta twiddles is injective. Finally, we need to show that theta twiddles is surjective. So we want to show that everything in the image of theta gets hit by some left coset here. Well, that's sort of clear. So if we're given theta of g in the image of theta, because remember, everything in the image of theta is theta of g for some g, we have that theta twiddles of g cur theta, this left coset, is theta of g. So theta of g is contained in the image of theta twiddles. So combining all of these bullet points, we discover that theta twiddles is an isomorphism, and so this quotient group G quotiented by the kernel of theta is isomorphic to the image of theta. This is an incredibly fundamental theorem in group theory. We use it all the time. It has various interesting consequences. So for example, we know from Lagrange's theorem something about the size of this quotient group, so we can use that to write down a relationship between the size of a finite group and the size of the kernel and the size of the image, which you might like to compare with things we've seen in linear algebra, for example, like rank nullity. It's incredibly helpful also for telling us about the structure of homomorphisms, telling us what maps conceivably can be homomorphisms, because we know that we have to have this property. And it also gives us a strategy for showing that a quotient group is isomorphic to something. So in general, it's quite fiddly, because as we've seen, we have to worry that it's well defined and so on. But if instead of showing that directly that this quotient is isomorphic to something, we write down a suitable homomorphism of the right kernel, then we can apply the first isomorphism theorem and we're in good shape.